Welcome to the next lesson in the Earth and Space topic. We are covering gravity in space today, folks. Right, we're going to start off with confused.com today. We've got a few characters coming up and they've all got questions or things that they are confused about regarding gravity in space. So it's going to be your job to, through this lesson, be able to help them out. So, does the force of gravity act in space? This gentleman's asking as he raises his eyebrow there. Very interesting thought. I'm pretty sure only large objects like stars or planets exert a force of gravity. We'll certainly be covering that one in this lesson. What is the unit for measuring gravity? He thinks it's the Newton. Is he right? We're going to find out. Well, indeed, Bart. What are you doing here? I've no idea yet. Maybe I should have found a picture of Lita instead, but never mind. Welcome. Would I weigh less on the moon? I could eat more cheese on toast, and the moon is made of cheese. He's thinking, well, oh dear, dear, dear. Clearly, we're going to have to spend a bit of time with him, everybody, trying to clear up a few misconceptions that he's got. And could you jump higher on the moon? Oh, he's cute, him, isn't he? Well, we're going to find that one out if we think about that in a short while in the first objective. Aye, sorry, mate, I'm not looking at you there. I won't want to upset you. You know what they're like, them small dogs. They can be quite vicious. What on earth is going on here then? Well, one of Einstein's most famous quotes is, you might have heard this before, God does not play dice with the universe. Now, I'm pretty sure that's not what he had in mind when he made that quote. He wasn't referring to an actual God in terms of the creation of the universe and some sort of master plan. He was actually expressing his confusion at the time about new ideas that came through on quantum physics, and he struggled with those concepts. And he brought that quote out in relation to that. Nothing to do with God. Okay, building site time again, folks. Work in progress. What is it that we need to get through in this lesson? 3 objectives that we're going to cover. First one, state the direction gravity acts and describe differences between mass and weight. Things that we need to get into your head at this stage, boys and girls. Mass and weight are not the same. What factors affect the strength of gravity? What is gravitational field strength? How do we use it to calculate the weight of an object? That's our second objective. And the last one we'll get to, recall that planets and satellites are kept in orbit by gravity. And again, we're going to look at differences in orbits of artificial satellites that we've got up there orbiting our own planet. So there we go. There are objectives for this lesson. Let's roll our sleeves up. Let's get stuck in. Okay, so we're on our first objective here. You're going to need a pen and some paper to be making a few notes and certainly to do some calculations as we go forward. So please make sure you've got that ready if you haven't already done so. So, meet John. He's not happy with what he sees on the scales. Hi, John. Yep, all right, mate. I told you to lay off them deep pan pizzas in lockdown, didn't I? You wouldn't listen. Anyway, as a result of them pizzas, John's mass is now 90 kilograms. And we're going to use that information to calculate his weight if he was on Earth, which he is, of course, if he went to the moon, and if he went to the International Space Station. We're going to need some extra information before you can make those calculations. I'll share that with you now. Now, the gravitational field strength in newtons per kilogram on Earth is 10. Gravitational field strength on the moon is 1.6. Take a minute to think, why is less on the moon? That should be clear to you. Gravitational field strength on the International Space Station is 0. Now, of course, it tells you there that the gravitational field strength of a planet or a moon is measured in newtons per kilogram. Yeah, you were halfway there, mate. Not too bad. You said the Newton. It's certainly to do with the force, but it's to do with the force of gravity pulling down on mass. And of course, the unit of mass in physics, boys and girls, is the kilogram. So we talk about gravity in terms of the amount of force pulling down on every kilogram of mass. So therefore, the unit is the Newton per kilogram. Now, here's an equation that you're going to need finally, and then you can make those calculations. The weight of an object is calculated by multiplying its mass in kilograms by the gravitational field strength of whatever planet or moon that it's on. Have I got those questions now? You should be able to work them out. I'll share the answers with you in 3, 2, and 1. So on Earth, if we have a look, again, his mass is 90 kilograms. So again, 90 multiplied 10, which is the gravitational field strength for the Earth, gives him a weight on Earth of 900 newtons. On the moon, again, he's still 90 kilograms. He's still John. He's still the guy that ate too many pizzas. So his mass hasn't changed, has it? But what has changed is the force of gravity pulling down. So on the moon, he would only have a weight of 144 newtons. Take John to the International Space Station. I'm sure he'd feel quite happy floating about there. Multiply his mass, 90 kilograms, by 0 because there's no gravitational field strength there. So therefore, he's weightless. And again, we associate that, don't we, if we think about it being weightless as being in space, i.e. not on a planet. Okay, we've covered some key things there. And again, we'll spend a bit of time thinking about them in more detail on the next slide. Your turn, 6 statements, straightforward enough, sort them into whether they have to do with mass or whether they have to do with weight. Have a go at the extension as well. Hopefully it should help to clarify your thoughts on the difference between mass and weight. Answers in 3, 2, and 1. Measured in kilograms, of course, is to do with mass. The kilogram is the unit of mass. Force caused by gravity, again, that is weight caused by the force of gravity pulling down on your mass. Affected by gravitational field strength of a planet, again, that's to do with weight. The bigger the planet, the greater strength of that gravitational field. Measured in newtons, of course, is weight. It's to do with force pulling downwards. Total amount of all the atoms that make up your body. Again, add up all of those atomic masses, and that makes up you. It's to do with mass. Same value anywhere in the universe, of course. That's got to be to do with mass. You can go anywhere you want in the universe. You're still you. Therefore, it's got to be to do with mass. Scientifically, if you are weighing yourself, you should really say you are recording your mass. All the scales are doing is giving you a mass that's caused, or a reading that is caused by the force of gravity pulling you down on them scales. If you were to go to the moon, you'd still have the same mass. You'd be being pulled down with less force, and therefore you would be registering less weight on the scales. There are differences. Be careful how you express that. But as I've said, you should say you are recording your mass. Okay, science is all about analysing data and looking for patterns. So have a look at that. Can you put some sort of order into the information that you've got there in front of you? Is there something other than diameter that might affect the gravitational field strength at JAF as it is there in the table of a planet? And can you summarize the questions into a short paragraph regarding the information that you can see on that table? Answers or my thoughts coming up in 3, 2, and 1. Well, as you can see, a general rule, the bigger the diameter of the planet, the greater its gravitational field strength. But look at it carefully, there are exceptions. You should hopefully be aware that planets, or outer planets like Saturn and Uranus and Neptune, they are much bigger than the Earth and Venus. However, their gravitational field strength is actually a little bit less. So we've also got this idea of the density of the planet. Hopefully you're aware those outer planets are what we call gas giants. And of course that gas has a lower density than the inner rocky planets. Interesting fact, if you could get a planet big enough with an ocean big enough, and you could get Saturn to sit in that ocean, because it's less dense than the water, it would actually float. Imagine waking up to that view in the morning. Fantastic. I'd like you to work through this one. I'm not going to say too much. Obviously, the circles represent planets. The arrows represent the force of gravitational attraction between them. And I'd just like you to use those diagrams. There are 2 factors that you should be able to grasp from that that affect the force of gravity between 2 objects. Have a think about that. I'll share my thoughts with you in 3, 2, and 1. So from the top diagrams, we can clearly see that the greater the mass of the planet, the greater the force of gravitational attraction between those planets. And again, underneath from the second diagrams, we can clearly see that if those 2 planets are further apart, then that force of attraction between them is less. Please note, I've got the arrows there coming from the center of the mass. That's really important in a force diagram, which is what this basically is, because that force of gravity, just like it's trying to pull you to the center of the Earth, that's because that force of gravity is acting from the center of the Earth's mass. Very important. Good job we're on a planet with a crust. Otherwise, clearly, if we were on a gas giant, for example, we'd just be pulled further and further inwards. Continuing on a rocket theme, you can't do too much about space without thinking about rockets, especially in terms of our understanding of space and exploring it. There are a couple of paragraphs there. I'd like you to have a think through. Again, if you want to copy that out, fill in the missing words, but at least make sure that you've worked out what the gaps are. Extension underneath to give you something extra to think about. What are the missing words, sir? Well, there they are. Off you go. I'll share the answers with you in 3, 2, and 1. So, force of gravity between two objects depends on the mass of the object and the distance between them. Hopefully we've got that from the previous slide. The greater the distance, then the weaker the force of gravity between them. Spacecrafts have to produce a large force. That's what we refer to as the thrust from the engines, and that's got to overcome the force of gravity, which is trying to pull down its mass. Don't forget rockets, especially at the start with all that fuel, they have a very large mass. Now, as a spacecraft gets further away from the Earth, the force of gravity gets weaker. Now, that leads us into that extension bit at the bottom, doesn't it? As they get further away from the planet, the force of gravity trying to pull it back down gets weaker, and therefore the thrust from the engines needs to be less. So you can get rid of your earlier booster rockets, remember those SpaceX ones from a previous lesson, because you don't need them anymore. And you can just have your main booster that's just propelling whatever it is that you're trying to get beyond the Earth's or gravitational field. So again, that's a good one there to help you understand in terms of the strength of gravity and how it gets weaker as you go further away from the planet. Something for you to think about on this one. Have a quick read through, and again, I'll go through the answers with you in 3, 2, and 1. First one, of course, is W, clearly because they are close together. Same mass as those in X, but they are close together in W. And explanation, of course, on the second one, Z, of course, because the mass is greater. Be careful. If you look carefully there, you'll see in Z, the mass is 100,000 kilograms, not 10,000 as it is in Y. Look carefully at the information they give you in questions. Your turn still. Have a look at these. This time, I want to think about it graphically in terms of the relationship between the force of gravity and mass and the force of gravity and distance. So as I'm asking you there, sketch a line on each graph to show the effects of increasing mass and distance on the force of gravity. Answers in 3, 2, and 1. So for mass against gravity, we've got an increase going up, or a linear line going from the origin, directly proportional. And again, what we can see clearly, as you increase the mass of an object, its gravitational field strength also increases. And again, for distance, we can see clearly as the distance from an object increases, then the force of gravitational attraction of that object on something else will decrease. Straightforward enough, hopefully, on that one. One last bit of data analysis to get us through that second objective. Have a look at the data there in that table. What's the relationship between the distance from the sun and the speed of the orbit? And again, an extension, why are there two distances for each planet? I've only used 3 there just to save time and space. Obviously, the same pattern would fit if we put the other planets in between. So have a go. 3, 2, 1. Answers coming up. So we can see that as the distance from the sun increases, that the length of the orbit also increases, and that the speed also is less as it makes that orbit. Why are there two distances for each planet? Hopefully you can remember from a previous lesson that the orbits of planets are not perfectly spherical. They are elliptical. So there's going to be a point in the orbit whether it's further away. There's going to be a point in the orbit where it's closer to the sun. A couple of good words in there for you. The aphelion, of course, is when it's closest, and the perihelion is when it's at its furthest point. You can try this in your garden if you want. All you need is a tennis ball, piece of string. Tie the tennis ball to the string somehow. Make sure it doesn't go flying off. But as you spin the ball on the string, the closer it is to you, you'll notice that the faster the ball is going. If you extend the length of the string, you'll clearly see that the orbit of the ball around you takes longer. You could also think about this in another way, in terms of the amount of effort you have to put in. If you're spinning it on a very short piece of rope, how much effort do you have to put in compared to if you were spinning it on a very long piece of rope? How could you kind of relate that to the idea of bigger stars being able to have larger gravitational field strengths? I'll leave you to think about that one. We've made that final objective a bit close to home. We're going to look at satellites and different types of satellite, but let's link the satellites that we can see in that image to what we've thought about already in terms of the orbits of planets. So how do man-made satellites that are orbiting the Earth compare to natural satellites, i.e. planets, which are orbiting the sun? Again, be clear on that definition. A satellite is something that orbits a body in space. So the moon is a natural satellite of Earth, and these things that we can see here are man-made or artificial satellites. So how do the orbits compare? Hopefully you've got this idea that just like planets, the closer the satellite to Earth, then the faster its speed as it orbits the planet. We've put a lot of satellites out there, folks. I want you to spend a little bit of time on this slide thinking about them. We've already thought about that definition there on the previous one, but again, be dead clear on it if you're not, make a quick note. So planets are natural satellites of a sun or a star, whereas we have artificial satellites, which we have put up there to orbit our own planet using rockets. Don't forget from previous lessons, we've also got lots of satellites orbiting the other planets in our solar system, studying them for us. So some questions for you. So why do we use geostationary satellites for GPS? Why are elliptical orbits used to communicate the parts of the Earth nearer the poles? And explain why satellites in polar orbit will eventually pass over all parts of the Earth. Answers in 3, 2, and 1. So, as we can see, as it orbits, it's orbiting at the same speed that the Earth rotates. And that diagram actually quite clearly shows it, doesn't it? It's always looking down on the same part of the Earth. And therefore, you can always communicate upwards to it in space, and it will always be there to send you a signal back down. For the second question, again, they spend longer over the poles if they're in that elliptical orbit. Don't forget, as it goes round, as we can see as it comes up here now, at one part of its orbit, it's on the other side of the planet, and therefore you can't communicate with it. So as it does that elliptical orbit, there is a longer period of time where it can communicate with places nearer to the poles. And again, for the final one, a polar orbit, as it's orbiting around the poles, the planet is rotating beneath it. So it's constantly moving over the surface of the Earth, or should I say that the surface of the Earth is rotating beneath it. So it's always covering different places as it makes that orbit. So a lot of different satellites out there, and again, there's a lot of them. Did I mention there was a lot of satellites out there? Have a look at this. Beautiful image, not to scale, of course, but it gives you an idea. A lot of them satellites don't actually work anymore, and we now classify them as space junk. And one of the things that NASA does is to monitor all of that space junk out there. We need to know where it is. We don't want it bumping into other stuff we put out there or crashing into the International Space Station. Quite a phenomenal image, I think. I'm sure this chap needs no introduction. Einstein, as it says there, he took Newton's earlier ideas on gravity to a whole new level. Don't forget, we've mentioned previously, Newton was the first guy to theorize about gravity in terms of something that we could quantify and try and understand. Einstein, as I said, a few hundred years later, saw things entirely differently. If we have a look at that rather curious image there, what it actually shows is his idea that the mass of an object in space, be that a planet or a star, the mass of those objects warp the fabric of space-time. Now, it's a very similar kind of idea. Imagine sitting in the middle of a trampoline. Your mass causes a depression in the fabric of that trampoline. And again, if you've got a tennis ball, you could get it to go in a circular motion around the depression in that fabric due to your mass. Similar kind of thing. And again, we can see here, same process, the warping of space-time caused by the sun again causes the Earth to orbit around it. Could I just stress all this stuff about Einstein is just things I'm putting in, hopefully because you find it interesting. I hope you've not been hypnotized by that image yet, but what on earth does it represent? If you think back to the previous slide, the sun warps space-time more than the Earth, and the Earth warps space-time more than the moon, because again, we've got differences in mass. But what on earth would have enough mass to warp space-time that much? So you've got an idea, but what on earth might be down there at the bottom of that gravity well? I'm sure you worked it out on that previous one. Black holes, they're out there. We know for a fact. Now, black holes, as it's telling you a bit there, you might know a bit about this already. They are formed when supermassive stars collapse in on themselves. And when I say supermassive, I mean supermassive. Our sun is relatively quite small when you look at some of the stars that are out there in our galaxy and beyond. So, as they collapse back in on themselves, if they collapse in enough, they form black holes. Now, we've got a problem spotting them because black holes are black. And again, space is black. So how do you see a black object against a black background? It's a bit like looking for a white cat in a snowstorm. It's a bit difficult. So how do we do it? Well, one of the ways that we've found is by observing the effect that a black hole's gravity has on light reaching us from distant objects in space. See it quite nicely on the image that I've got there repeating for you. And as the light comes past the black hole, it is warped. And again, Einstein thought about this. He called it gravitational lensing. Now, the reason a black hole is black is because even light can't escape its gravitational field because the mass of a black hole is that great. And that's why it's black. It doesn't reflect light, so you can't see it. Imagine if one got close to our sun. I want to stress it's very, very unlikely. But as you can see there, the mass of the sun would just be drawn into that tiny black hole. You can see those jets coming up from the north and south pole of that black hole. And again, what they are bursts of electromagnetic radiation full of things like gamma rays. You don't want to get caught in one of them. As far as I'm concerned, this would be the best excuse ever for not doing your homework. Sorry, sir, I'm being dragged into a black hole. Right, as it says there, we have an actual picture of a black hole. Now, as I said previously, don't forget the black hole is black hole because even light gets dragged into it. So you can't actually see the black hole, but what you can see is the stuff around it getting dragged into that black hole. Now, we call that the accretion disk. So that orangey red kind of disk that you can see there around the black hole in the center is a lot of stuff that's being dragged into that black hole, and you can just see that clearly across the distances of space because of the amount of energy that it's giving out. Now, massively interesting fact there. If you had a black hole with a radius of 1 centimeter, it'd fit on a spoon, and that would have the same mass as the Earth. It's kind of unimaginable, really, just how dense the matter in a black hole is. Okay, one last thing for you to do. We've had a bit of a distraction for a few minutes there, thinking about the wonder that is a black hole in space. So what can you recall from the different parts of this lesson? So again, mix and match. We've got 8 statements there, and opposite to that, we have got the end of each sentence. So clearly, it's your job to match those up. Off you go. Answers coming up in 3, 2, and 1. Okay, so gravitational field strength is, of course, the force of gravity on every kilogram of mass. Gravity pulls things down towards the center of the Earth. If 2 objects are moved apart, the force of gravity between them is weaker. If you take something to the moon, its weight will decrease, but not its mass. That stays the same. And again, number 5, force of gravity between 2 objects. It's bigger. The objects will have more mass. The gravitational field of the Earth is the space around it where it can affect other objects. The Earth's gravitational field strength is 10 joules per kilogram, and the moon is kept in orbit, of course, by gravity. Hopefully you did okay on that one, folks. Just check your answers. Right, you've made it to the end, folks. Thank you very much. I'm just going to leave you with a couple of images. Beautiful one there of the International Space Station. there have been recently images released on YouTube, actual live stream videos of people doing spacewalks, maintaining and, of course, developing the International Space Station. Honestly, absolutely fascinating. Have a look. Now, let's just think about life on the space station. Here's an interesting one. What we can see there, again, is a indigestion tablet being inserted into a drop of water. Fascinating that we can see the little bubbles of carbon dioxide being created, and they're being contained within surface tension of that bubble as it floats around there in zero gravity. Quite unbelievable. And secondly, clearly, it's a bad hair day every day on the International Space Station. No, I've got no idea either. But again, it proves that you can't trust everything you see out there on the internet. I do like it though, and he has got spacewalk coming up in a minute. Here we go. Check that out. Well done, lad. Okay, folks, again, thank you very much. You've made it to the end. I'll speak to you soon in another lesson.